If you tie a ball to the end of a string and start to spin it around in a circular path, you will have created something known as a conical pendulum. Now, the faster you spin it, the greater this angle theta will become. And you can argue that it's not possible to spin it so that it goes completely flat. You can get close to this, but the reason you could never get the string completely horizontal is because, well, if you did, there'd be tension pointing straight toward the center of the circle, and that's fine. Something's providing the necessary centripetal force, but there's also this downward pull of gravity, and then there's nothing to counter that out, right? However, as long as the string makes some angle theta with vertical, then the free body diagram would look something like this. Tension, oops, try that again. Tension pulls up at an angle, gravity pulls straight down. So this is our unresolved free body diagram. If we make an x and y axis, and notice that the motion of the ball is entirely within the horizontal plane, right? So that its centripetal acceleration points along the x-axis. So we don't need to do anything to the force mg. However, the tension should be resolved into components. And by the way, notice that that theta is the same angle as indicated in the picture above, right? I think if we draw an imaginary vertical line, these are what we call alternate interior angles. So pointing up is a component of tension that lies adjacent to that angle in this pictured right triangle. So this would be T cosine theta. We often associate cosine components that are found by calculating cosine with x-axis components and sine with y-axis components. That's because most often we measure the angle off of the x-axis. But here's an example where we're measuring our angle off of the y-axis. So the role of sine and cosine might be reversed from what you normally associate. Okay, so then there's a component pointing in toward the center of the circle found by multiplying tension times the sine of the angle. And we would probably guess that T cosine theta and mg cancel each other out, because like we say, the acceleration points entirely within the horizontal plane. There's no vertical component to the acceleration of this rotating object. So you see, if these cancel each other out, then that only happens if T cosine theta in magnitude is equal to mg. So you're left with this unbalanced amount of force. Right? There's no other force back this way to cancel it out because it's not in equilibrium, right? That unbalanced force, T sine theta, is there to provide the centripetal force. And to be clear, let's make sure, I think I've stated this before, centripetal force is not a force in and of itself. It's not as if there's a component of tension pointing up called T cosine theta, a force of gravity down, mg, an inward component to tension T sine theta, and then in addition there's some type of force called centripetal force. No. T sine theta is pointing toward the center of the circle, so T sine theta is the centripetal force, right? Centripetal force is not a force in and of itself. Any force could happen to be centripetal. So the net force, the amount of unbalanced force in this case, is T sine theta, but we get to replace that with ma. But this is a centripetal acceleration, so we can actually replace this with mv squared over r. So what I'd like to do is divide one equation by the other. Actually, let me rewrite it so that we have sine over cosine. If we divide this way, t cancels out, and sine over cosine is tangent theta. And we divide the right side of the equation, m cancels out, and we're left with v squared over rg. So v would be the square root of rg tangent theta. All right, what if we were interested in angular speed instead of tangential speed? Then we could write the equation tangent theta is omega r quantity squared over rg, which is omega squared r squared over rg. We can cancel one of the r's. And so we get an equation that says omega is the square root of g tangent theta divided by r. What if instead we were interested in the time it takes to complete one full revolution? Okay, well, angular speed is equivalent to saying one revolution in one time period. Or in other words, it's 2 pi radians in some number of seconds we identify as capital T, the symbol for period. So we can substitute in this regard and say 2 pi divided by T is the square root of g tangent theta over r. We could invert both sides of the equation and square it. So T squared divided by 4. Well, is this the way to do it? No, I guess we don't need to square both sides. Let's just invert both sides. T divided by 2 pi is equal to the square root of r over g tangent theta. Or in other words, T is equal to 2 pi times the square root of r over g tangent theta. So what if you had a special case where the angle is 45 degrees? And you had the length equal to exactly 1 meter. Then what would the radius be equal to? Well, you can see that this is a right triangle, so r would be equal to L times sine of theta. Okay, so if we make a substitution, then T would be 2 pi times the square root of L sine theta divided by g tangent theta, but tangent is the same thing as sine over cosine. So sine would cancel out, and we would have T equals 2 pi times the square root of L cosine theta over g. Okay. And given these exact numerical values, if the length is 1 meter and the angle is 45 degrees, then the period should be equal to 2 pi times the square root of 1 meter times the cosine of 45 degrees divided by 9.8 meters per second squared. Meters cancel, and you can see the units overall for the period is going to be seconds. So grab a calculator and see what we get. We get a period of about 1.69 seconds. So how long would it take to spin it around for 10 complete revolutions? I guess that would be equal to 16.9 seconds. So I believe in this unit of study, you'll have the opportunity to do a lab in which you construct a conical pendulum, and you can make it so that the length of your string is exactly 1 meter, and you can try to spin it so that the angle is 45 degrees, and you can see how much time it takes for 10 revolutions. Okay. Or conversely, if you choose to make the length of the string greater than 1 meter, so that the radius on the ground is 1 meter, whatever the case is, you can use this formula and plug in the given values to make a prediction of the amount of time and then spin it and see if it actually works out. So there you have it. Yet one more example of applying Newton's laws to uniform circular motion. In some cases, we have friction as the centripetal force. That would be like the car driving around on a circular racetrack. What's allowing the car not to follow the law of inertia and continue in a straight line and instead go about a curve? Friction is a force that points toward the center of the circle. We've studied roller coasters. When a roller coaster cart goes through a circular loop, what force is pointing toward the center of the circle? Well, there's at least one, mg, and if the roller coaster is going fast enough, along with mg, there's some normal force. So centripetal force can be provided by friction, or it can be provided by a combination of two forces in the form of normal force plus gravity. And then in the case of the conical pendulum, we have a centripetal force that's provided by a component of the tension. T sine theta is the centripetal force. So there are a lot of examples of centripetal force being provided by different types of force you're already familiar with. The end result is still to apply Newton's second law. By studying a free body diagram, you can determine what the net force is, and we always set net force equal to ma. In the case where the acceleration is centripetal, then I guess we're setting net force equal to mv squared over r. So, thanks for watching, and continue to tune in to further example problems in our study of centripetal force.